For number 10, we have a scenario here. A paint manufacturer wants to find out the average amount of paint that his machine is actually putting into the cans that it fills up. And so we want to estimate that average that it's putting in within a certain margin of error. And we're assuming we have a normal distribution. So we want our estimate of the average to be within a certain margin of error. And so we're going to determine the minimum sample size needed to construct a confidence interval, a 90% confidence interval, that's going to be within that margin of error. And we are told what the population standard deviation is. In 6.1, the formula is given to find the sample size needed. And we just need to plug our values into this formula. The one thing we need to calculate is we need to find the critical value associated with 90% confidence. So recall that what we're looking for is the critical values where 90% of the normal distribution will be between those critical values, which means that 10% of the distribution would be outside in the tails of the distribution. So 10% total in the tails would be 5% in each of the tails. 5% in each of the tails, and then 90% in between our critical values. So in Excel, we can use equals norm.s.inv. We want the critical value associated with 5% being in the tails, and Excel gives us that value. Now, using that formula for the minimum sample size, it's that critical value multiplied by the population standard deviation, and then divided by the desired margin of error. After you get that result, you need to square the result. And I typed this in separately in Excel. It's easier for me to do it that way. You could type it all in as one formula here with the exponent squaring it. I like to get the answer and then come over here and take the answer and square it. I think there's less chance of making a mistake typing it in when I do it that way. So squaring that result, I get that the minimum sample size would have to be 3.4. Now, we need at least 3.4, but we need a whole value. So we would always round up to the next closest whole value. So 4 is our minimum sample size. So after finding the minimum sample size needed, in part B, we're told we have a sample. In this example, it's of size 6. We're told what the mean is of that sample. And we want to construct a 90% level of confidence. And we're again told what the population standard deviation is, which lets us know we can use the normal distribution. The first thing we need to do is construct a confidence interval. And here's the information given from the problem. And in Excel, we can use the formula equals confidence.norm. And that's going to give us back the margin of error that we need to construct our confidence interval. The first thing you need to type in the parentheses is alpha, which is 100% minus the confidence level. So 90% level of confidence, alpha is 10% or 0.1 as a decimal. And then you want to type in the population standard deviation. And then the last thing is the sample size. When you do all that, Excel gives you back the margin of error. That's how you construct a confidence interval, is you take the margin of error, you add it to the sample mean to get the upper limit of your confidence interval, and then you subtract it from the sample mean to get the lower limit of your confidence interval. So we are 90% confident that the population mean lies somewhere in between this lower limit and this upper limit. So after entering in our confidence interval, the follow-up question is, does it seem possible that the population mean could be exactly 128 ounces? Well, 128 is outside of our interval that we are confident the mean lies somewhere in between these values. So it doesn't seem possible that the mean would be exactly 128 because it is outside of our confidence interval. Number 11 is similar to number 10 at the beginning of this video. We have a manufacturer here who makes soccer balls, and he wants to estimate the population mean for all the soccer balls that are made within a certain margin of error. And first we're going to determine the sample size that would be required to construct in this example, a 99% confidence interval for that population mean. And we are told the population standard deviation is this value here. And since we have the population standard deviation, we can use the normal distribution. From chapter 6.1, we have the formula that we're going to need to use here to find the sample size that we'll need to create the confidence interval that we're looking for here. And the one part we need to work to get is the critical value associated with our level of confidence. And so with a 99% level of confidence, we're looking for critical values that'll have 99% of the normal distribution in between them, which leaves just 1% of the distribution to be in the tails. Now split between both the tails, that's just 0.5% in one tail and 0.5% in the other for a total of 1% in the tails. So in Excel, we can use the formula equals norm.s.inv and 0.5% as a decimal, 0.005, and that gives us the critical value associated with 0.5% in the tails. Now using that formula for the minimum sample size, the formula said to take that critical value, multiply it by the population standard deviation, and take that entire result and divide it by the margin of error. Then that result should be squared. So taking that answer, I'm going to square it. And this here is the minimum sample size needed to create the confidence interval that I want here with the given level of confidence and the given margin of error. You can't have 93.3 in your sample. We need a whole value. We have to round upwards, so we have at least 93.3, so 94 would be the minimum sample size. So the second part of the problem says we're taking a sample size of 103. It tells us the mean of that sample, and we're going to create a 99% confidence interval. And again, we're told what the population standard deviation is. So here's the information from the problem. In Excel, we can use this formula right here, equals confidence.norm. You enter in alpha, which is 100% minus your confidence level, so it's 1% here as a decimal, 0.01. Enter your population standard deviation, and then the third thing you enter is your sample size. And that gives you back the margin of error for creating your confidence interval. Now, the confidence interval always has the sample mean in the very middle of the interval. Then you add your margin of error to the sample mean to get the upper limit of your confidence interval, and subtract the margin of error from the sample mean to get the lower limit. And so we're 99% confident that the population mean lies somewhere in between this number and this number. And the final part of the question says, does it seem possible that the population mean could be less than 27.2 inches? Well, looking at our confidence interval, 27.2 inches is inside of our upper and lower bound. And so being less than 27.2 inches is totally possible. We're 99% confident the mean lies somewhere in between here. So sure, it could be 27.2 because that does fall somewhere within our confidence interval. Number 12 is saying if we change nothing else at all, how does changing just one of these variables at a time affect the minimum sample size requirement? And so in 6.1, we're seeing how changing just one of the arguments here in this formula would affect our result for the minimum sample size needed. If we increase the level of confidence, that will increase the minimum sample size required. Increasing the level of confidence makes the top part of this fraction larger because our critical z sub c here gets larger. And so the value here gets bigger, which means our result, the minimum sample size needed, gets larger. That should also make sense if nothing else changes and we want to get a higher level of confidence. The only way to do that is to get more data, more information, which we get from increasing the sample size. If nothing else changes and we increase the error tolerance, that will decrease the minimum sample size required. Again, looking here at the formula, that's saying nothing else changes, but we're increasing our margin of error here, E, that we're dividing by. If you divide by a larger number, the overall result is smaller. So we'll get a smaller value for N, the minimum sample size. And that should also make sense even without looking at the formula, because a larger sample size gives us more information, makes things more accurate, and we can get a smaller, tighter, more precise confidence interval. So if we're willing to increase the width of our confidence interval, increase how wide it is, and not change anything else, then we don't need as big of a sample size because we're willing to have a wider, less precise confidence interval. And lastly, increasing the population standard deviation. Again, that is making the top part of the fraction larger, which makes the overall value larger. So our minimum sample size result will be larger, it will increase. And without looking at the formula, if our data is more spread out, that's what a larger population standard deviation would mean, then we're going to need a larger and larger sample to get a more precise, honed in confidence interval for a smaller range of numbers to estimate the population mean. So more spread out data means we're going to need a larger sample.